Compounds that have molecules of water attached to them more or less permanently are known as hydrates, and they're pretty common in nature. Gypsum, for example, is what we call calcium sulfate as a hydrate. Gypsum has a ton of uses, from an ingredient in cement and pottery to being the primary component of your walls, as a material more commonly known as gyprock. But exactly how many water molecules will stick to this or any other hydrate for that matter? Each hydrate is different, but in today's experiment you'll learn a technique that will actually allow you to count the number of water molecules that are stuck, or non-covalently bound, to put it technically, to calcium sulfate, which is amazing. So how do we do that exactly? Well, let's remember that we can count molecules using the concept of the mole and Avogadro's number. For example, if I knew that I had exactly 1 gram of water, I can use the formula weight of water, which is 18.02 grams per mole, to calculate that I have exactly 0.056 moles of water, or roughly 3.3 times 10 to the 22 individual water molecules. So what I need to do with the hydrate is somehow count how many calcium sulfate molecules I have and how many water molecules I have, and then I can work out how many waters are attached to each calcium sulfate on average. The only problem is that the water is actually attached to the calcium sulfate, so here's what we'll have to do. We'll start by weighing how much gypsum we have. Then we'll heat it in order to evaporate any water that would be present in the sample. Weighing again, we'll notice that our sample got significantly lighter. This new mass is the weight of the dry calcium sulfate, also known as anhydrous calcium sulfate, and the difference between the previous mass and the new one corresponds to how much water that was lost. Since we know the formula weights of calcium sulfate and water, we can calculate how many moles of each we had. The law of multiple proportions tells us that the number of moles of water will be some multiple of the number of moles of calcium sulfate. If they're the same number, then there is only 1 water for every calcium sulfate. But if the number of water molecules is, say, twice as big, then there are 2 water molecules for every calcium sulfate, and so on. Simply dividing the number of moles of water by the number of moles of calcium sulfate will tell you what this ratio is, and you're done. Using tongs, place a crucible on a clay triangle and heat it by passing the flame of a Bunsen burner over all its surface, gently at first, and then beneath the crucible with the full flame for about 10 minutes. By doing this, you're trying to remove any atmospheric water molecules that might be adhered to the surface of the crucible itself. We'd like to make a very precise measurement, and so even the crucible has to be perfectly dry. Also, it's important to use tongs whenever you handle the crucible, because even the oils from your hands can affect the mass measured on the very precise balances that we'll be using. As you're heating, sometimes you can see a black deposit forming on the crucible. This is carbon from the flame, and it can throw off your mass measurements later, so it needs to be removed. You can use the direct force of the flame to burn it off. Once you're done, allow the crucible to cool in air for 3 minutes, and then use the tongs to transfer your crucible to the desiccator. This desiccator provides an anhydrous environment for the crucible and other objects to cool, without having to be exposed to any water molecules in the air. After your crucible is cooled for 10 minutes, determine the precise mass of the dried crucible using the analytical balance. One thing to keep in mind today is to always use the same balance to weigh your samples. It just removes the possibility of variance between instruments, causing any error in your measurements. Now it's time to get your gypsum sample. So tear the weight of your crucible on one of the top loading balances, then add about 2 grams of gypsum to it. You'll need to know the precise weight of your sample for this experiment, so transfer the crucible to an analytical balance and record its weight to the full 4 decimal places that the instrument reads. The next step is to remove water from the sample by heating it. So place the crucible on your clay triangle and heat it with the Bunsen burner, very gently at first, and then with a full flame for about 10 minutes. After some time, the bottom of the crucible should have a red glow. At the end of the heating, leave the crucible on the clay triangle and allow it to cool in the air for 2 to 3 minutes. Then, using tongs, of course, place the crucible in the desiccator for about 10 minutes. Now that your sample is dry, reweigh it on an analytical balance to get the precise mass of the dry calcium sulfate. You'll use this mass to calculate the weight loss due to heating, and that should be all you need to count the water molecules that you had in your sample originally. Be sure to dispose of your sample in the waste container located in the fume hood, and then repeat the whole procedure, except for drying the crucible, with a second sample of gypsum. Any good experimentalist repeats their measurements to ensure that they are reproducible. Alright, to finish off this lab, remember that we need to figure out how many water molecules are attached to a calcium sulfate hydrate. We know the mass of our clean, dry crucible, and we know the mass of that crucible with our gypsum in it. So taking the difference between those two will give us just the mass of our gypsum. We also know the mass of the crucible and the sample after we heated it. That will allow us to work out the mass of water that we lost from the hydrate by heating it. So the mass of the hydrate minus the mass of the water will give us the mass of the dry calcium sulfate residue, and we can use each of those to work out how many moles of water and calcium sulfate we had. It's exactly the ratio of these numbers that determines how many water molecules were attached to the gypsum in the first place. Averaging your results will give you a final answer for X, and you'll have figured out for yourself how to count water molecules in a hydrate and solve for an actual chemical formula.